I feel like this table is getting closer and closer, so I am definitely going to trip over this chair, and it's going to be very funny. Okay, so last class, we just basically talked about vectors and geometry of vectors. Geometry. So remember, a vector is something that has direction and length. It's a line segment, basically, that points to something and goes along a specific direction. So we're going to start off with something that everyone is going to be very excited about. I can tell looking at everyone's faces. I get to make that joke because I love math, and I know nobody else does. So I get to be excited for everyone else. So we're going to start off with some algebra. So we'll just say some properties. So there are some properties here that basically tell us that vector addition and scalar multiplication work exactly how we would hope they would, right? That they interact nicely with each other. So the first one is that if you add vectors, it doesn't matter which order you do them in, right? Commutative property. Doesn't matter. The second one is the associative property. So that means if you add three vectors together and you have brackets involved, you can shuffle those around. So commutative, associative. Now, these are worth mentioning because when we start getting into, well, we as in people who study math, we're starting to get to the realm where these things aren't true. We can't necessarily have these. So actually, we're going to talk about one that does not satisfy this property, so that the order actually matters, where A times B is not the same thing as B times A. In fact, A times B makes sense, and B times A might not make any sense at all. You might not even be able to do it. So we'll get there. But the point is, these aren't just like, we don't just write them down and then people go, yeah, of course. It's like, no, they're not always true. But now it's time for some that are obvious. If you add the zero vector to a vector, nothing happens. Makes sense. If you take a vector and add its negative, you get the zero vector. Surprise. Scalar multiplication works pretty nicely in terms of vectors. So this is saying, hey, you got two vectors, add them up, and then multiply by a number. That's the same thing as first multiplying the vectors by that number, and then adding them up. Same thing, doesn't matter. Do it in whatever order you want. Same thing here, if you have two numbers and multiply them by a vector, this is saying add the numbers first and then multiply the vector. Well, same thing is true. You can multiply by the numbers and then add the vectors, right? Works either way. This, can't write, it's too late. This is saying, hey, if you've got two numbers times each other, times a vector, you can kind of shuffle them around. So ultimately what this is saying is that if you've got two numbers being multiplied in this, you can do it however you want. You can multiply the numbers first, or you can do them one at a time into the vector. Or you can pull stuff out, is what this is saying, right? You got a number inside next to a vector, you can pull it right out in front. Time for what I would say is also an obvious one. If you take 1 times a vector, nothing happens. Right? That makes sense. Okay, so like I said, this essentially gives us algebra. So let's simplify. Again, I hate that word, but it is what it is. The expression 4 times u plus 1/4 v plus 5u. So what this is basically saying is we can condense this down a lot, right? And it works exactly how you would expect. There's nothing, no tricks here. So this property says, hey, you got a number in front, you can distribute it in. So So this is going to be 4 times u plus 4 times 1/4 u, or 1/4 v, rather. And then, hey, we got a property that says you got these two numbers next to a vector, just multiply them together, right? A lot of people would just do that in their head, and that's fine. This is 4 times 1/4, which is 1. We also have a property that says, hey, those are the same thing. And now we can add these together. So 9u plus b. So we got this messy-ish looking thing, and we can condense it down nicely, right? This is all that these properties are saying, is that you can manipulate vectors however you see fit, generally. So we can also solve equations. Involving vectors. And it works, again, exactly the same, because these properties look very much like properties for numbers. So 3a minus 2b minus 2 times b minus x. Some just mess here. X plus b minus 4a. So in something like this, we want to solve for x, right? So let's go ahead and do that. So the same thing that we always do will work here. We just isolate x, right? When we're trying to solve an equation, we isolate the variable we're looking for and move everything else the other side. So how do we do that? We're going to use those properties, so we can distribute this just fine. 3 times minus 2 is minus 6. Minus 2 times b is minus 2b. Minus 2 times minus x is plus 2x. We don't have to do anything to this side. And now all we do is we just move x to one side. It doesn't matter. I'm going to pick this side, though, because if I do this, then there's not a negative number in front of x, which is nice. And then we're going to move everything else to the other side. So all the stuff without x gets shoved over there. Now, again, when we say move stuff over, that actually means, so to move x over to this side means subtract x from both sides. To move 3a to this side means subtract 3a from both sides, if that helps you visualize it. But this is a technique from high school, so I'm not going to worry too much about it. But the point is, we move everything over, and I'm not going to simplify things yet. So we've got the b minus 4a over here, and then we're going to move all that over. Minus 3a plus 6b plus 2b. And now we just collect like terms, right? X's go together. So 2 minus 1 is x. Let's put our b's together. So 7b, 9b. Put our a's together. Minus 7a. So whatever x is equal to those two vectors. So if we knew what those vectors were, we just solved this equation, right? So it works exactly like manipulating equations, and there's a reason why I'm driving the point home here with equations and vectors. One, there's nothing special about them being vectors. The same rules still apply as numbers. But two, stuff that looks like this is what linear algebra is all about. So we want to, talk about it a bunch. Okay, but this thing right here, something that looks like this in terms of vectors is actually very useful, and we actually give something like that a name. And that's called a linear combination. So a vector u is called a linear combination of the vectors v1, v2, v3, and there's some number of them. Doesn't matter how many, we're going to say there's k of them. If there are scalars C1, C2, C3, CK, so that, now, again, this is, I warned about this on Wednesday. The notation for linear algebra, it just gets kind of like this. There's a lot of subscripts and variables and stuff like that, which, bad news, a lot of programming algorithms are described this way too, in terms, because just think about it. Something like this, we are indexing by a number here, right? Well, a for loop indexes also, right? So it just comes up all over the place, where how do you indicate that you're iterating over a for loop? You use a subscript or a superscript or something. So this is, it's just this sort of notation comes up all over the place. But anyway, so that vector u that we're looking at is, well, it's a linear combination. So linear means numbers times variables, and that's it, and then you add them up. Right? That's what that means. Linear means just very, very simple multiplication and addition. Those are the only things we do. And then we just add it all up. And combination, well, combination, we somehow combine them. So we combine them in the obvious way. We put these numbers in front of these vectors and add them up. Like that. So again, this notation is overwhelming, but once you see examples of what I mean, it becomes less bad. A perfect example is X is a linear combination of A and B. So here, I'm going to write it like this. So in terms of this notation, X is standing in for our vector u, right? Minus 7 is our first C. A is our V1. 9 is our second C. It's just a number. B is our V2, right? So they just match up like that, right? Linear combination just means something that looks like this. So another example. So the vector 2 minus 4 is a linear combination of these two vectors. So why is that the case? Well, let's translate these into this. So this is our vector u. We're saying this is a linear combination of the other two things. So let's call this v1 and this v2. So what we're ultimately trying to see is, can we find C1 and C2 so that u, this vector here, is equal to C1 v1, C2 v2. Right? Okay, cool. Now let's unpack this notation a bit more. We know what u, v1, and v2 are. So we can go ahead and plug those in. So this notation u is 2 minus 4. v1 is 1, 2. v2 is 0 minus 2. Okay, cool. But our goal here is to find out what is C1 and what is C2, right? Those are the numbers. We want to find those numbers. So let's sort of collect stuff together a bit more. So we can multiply this in. We get C1 and 2C2. This goes in here and gets added to this. Well, that's a 0. This is minus 2C2, like that. Right? Again, this is just from multiplying these into the vectors and then adding them up, which we're allowed to do. And hey, this is two equations, essentially. This thing has to equal this stuff. And this has to equal this stuff. Oh, this should be a C1, sorry. So now we just have to try and use this information to solve. So, okay, right off the bat, this first equation tells us that C1 is 2. Right? 0 goes away and it's just 2 equals C1. All right, cool. So then, with that information, in the second equation, we know C1 is 2. So 2 times 2 minus 2 times C2. We can use this information to solve. Move this over, minus 8. And so 4 is equal to C2. Like that. So, point is, we just found what C1 and C2 have to be. So let's back ourselves up. Right here, we just found these numbers. So what that means is ultimately, can't write. This first number is 2. The second number is 4. Now let's actually make sure that's the case, or that it works. So 1, 2, plus 4, 0, minus 2. So, okay, do the first numbers agree? This is 2. This is 2 times 1 plus 0, so it's 2. Great. Second numbers, minus 4 on the left. So 2 times 2 is 4. 4 times minus 2 is minus 8. 4 minus 8 is minus 4. They agree. So yes, ultimately that means this is a linear combination of these two things. Why? Because we can find the numbers that go in here. That's all linear combination means. It means find these numbers, right? And this abstract definition just saying, well, we don't have to restrict ourselves to just 2 vectors, right? It can be any number of them. And the definition is the same, right? Just write them down like that. Okay, so that's a concept we're going to have to come back to. It just fits in naturally when we're talking about vectors in general to sort of write this down, but it will come up again, so I'll remind you of it when it comes up again. But this is one of the more important concepts in linear algebra, is stuff that looks like this, basically. Although, again, it won't look like this mess, right? We'll have like numbers and like we'll know what these vectors are and stuff like that, right? So we'll actually be able to work with it. But this sort of concept comes up a lot. Okay, so we have talked about the operations we can do on these vectors, right? We can add them, we can subtract them, we can multiply by a number, that sort of thing. There's some geometry. So we're going to talk about some other related. Well, one of them is an operation, and the other one is just a property. So we're going to talk about the idea of dot product and length. So first, let's start with the dot product. So if we have 2 vectors that look like this, So again, this is linear algebra stuff, right? This is just saying there's n components in it, right? N numbers go inside this thing. Then the dot product of u and v. So the notation, we call it the dot product because there's a dot, right? Dot product. So what we do is we just take the first component, multiply it with the second component, and then add it to the same thing with the second components, and then the third components, u3, v3, and so on until we get to un, vn. And these are numbers, so this is regular multiplication now. So, important distinction here. It's something that I try to emphasize. This is like it's not the multiplication dot, right? Like it's actually a little bit more. If you look at the digital notes, it stands out a bit more. So on Wednesday, I said we can add vectors, we can subtract vectors. There's not a meaningful way to multiply vectors because there's not really a way to make it work how we would hope multiplication would. It just kind of is missing a lot of properties that are nice. So you might be looking at this and being like, but Travis, we're using a dot, and this seems to be like some kind of multiplication for vectors, right? No, because if you multiply two numbers, you get a number back, right? If you multiplied two numbers and got a shape back, I wouldn't call that any meaningful operation, right? Well, it might have meaning, but it doesn't produce another number, which is what we want. So this is not multiplication of vectors because it's a vector dot a vector, and it gives a number. It does not give another vector. So note, u dot v is a number, not a vector. I would say this is the most common mistake students make at like any level. So if you're sitting there and you're going, man, this seems hard. I only have 30-2. Well, good news. People who've taken calculus before will mess this up. It doesn't matter. This is just a mistake that is very common. So what I'm saying is if you go to do this on something and you get a vector out of it, nope. It's supposed to be a number. So what you probably did is you did what people will think multiplication could be, where you just multiply these things together and get a new vector. Again, that doesn't really give multiplication. It's missing a lot of properties that we would hope for multiplication and doesn't really work very well in terms of what we would want multiplication to do with vectors. So we just don't do that. It gives a number. So let's just do an example, which I don't need this. I'll just write down some random stuff. So if u is, I don't know, 1, 2, 3, and v is -2, 5, 1, then what's u dot v? Well, there is a formula for it, but the formula isn't really necessary, right? Because it's just take these first two things and multiply them together, plus the second two things multiplied together, plus the last two things multiplied together. That's it, right? You can even just use fingers and do it in your head. So this is -2 plus 10 plus 3. So that's 11. Can't check my notes because I just wrote down random vectors. So thankfully, this is not too hard to do, right? The dot product is relatively straightforward to compute. But it behaves nicely, and we end up using it a lot, actually. for one very specific reason, and it's that this very bizarre sort of operation ends up having some geometry tied to it. I'm actually going to talk about that first, actually. So this operation has geometry. Because like I've said, for all of this vector stuff, yeah, sure, they're just a tuple of numbers, but they always have a geometric meaning behind them. So we defined the idea of parallel lines, right, in terms of vectors, and it matches our intuition of what parallel is. There's sort of two other notions here. There's also the idea of being perpendicular, right? So if these two lines have a 90-degree angle when they join, we call that perpendicular. And then, of course, it's neither of those. That's a bad example. Right? They just sort of cross each other in no meaningful angle. So like there's some angle there. So let's see if we can define this, right? Because we've defined this. So two vectors are called orthogonal or perpendicular, it turns out. If, and good news, the definition is very simple. It uses this dot product. If it's 0, then we say they're perpendicular or orthogonal. All right, so let's take a look at these two things. Are they perpendicular? No, because the thing wasn't 0. Now, we have this definition here, and this gives us sort of like the way to compute it, but we are using a word that has a very intuitive meaning, right? This idea of perpendicular, this 90-degree angle. So whatever this is, better match this, right? So let's just think here. I'm just going to draw two vectors. So this right here is the vector 2, 2. Let's call that u. And let's do sort of half the length. This is 1 minus 1. Right? So looking at this picture here, we agree that these are orthogonal, right? Perpendicular in the intuitive sense. It looks like that, right? There's a 90-degree angle between them, right? So that's perpendicular. So let's see if this definition matches this one. So this thing, 2, 2, dot 1 minus 1. And so this is, when I write it like this is why students tend to mess it up, because you'll just go 2 times 1 and then this, and then you write it as a vector. Again, it is a number. So 2 times 1 plus 2 times that minus 1. So that's 2 minus 2, which is 0. Okay, that's good news, because that means this new definition we just had in terms of these dot products matches the intuition here. So just drawing some attention here. One of the reasons why in math we do this, so you look at this and it's kind of funny. We have two words that seem like they mean the same thing. They kind of don't, in the sense of perpendicular. If I go to my mom and say, "Hey mom, what does it mean for two things to be perpendicular to each other?" She probably knows, right? She might not be able to put it in math words, but she would be like, "Oh, if you got stuff that looks like that, right? Like they stick out of each other." And I'd be like, "Yeah, right. Good. That's what perpendicular means." We don't want to lose that meaning, right? That intuition. So that's a lot of the reasons why we make new words in math, because perpendicular, really, when we think about it, means stuff that is kind of laying flat, right? Like line segments. But in terms of this generalization, we want to talk about stuff in like R6, right? 6 dimensions, 8 dimensions, doesn't matter. So calling it perpendicular when you can't even imagine what it looks like feels kind of wrong, right? Because now we're sort of using a word that has intuition to mean something else, So that's what we call it orthogonal, because then we get to keep that same meaning, that intuition, but connect it to a more generalized idea. So if I went to my mom and said, "Hey, mom, what does orthogonal mean?" She'd be like, "I don't know, Travis, leave me alone." But she probably knows what perpendicular means, right? Just because it's a word that we just use sometimes intuitively. So that's why we usually do that in math. Ultimately, the reason why is because we want to not confuse people, which is funny because the opposite is what ends up happening when people are learning it for the first time, because they're like, "Hey, wait, what? That's two words for the same thing." And it's like, well, yes, but no. This word means the intuitive thing. This means the more generalized concept. So it's okay. So this dot product ends up behaving pretty nice. It has this geometry, but it also is just an operation we can perform, right? And it has some nice properties. And ultimately, these properties just say, hey, dot product's nice. It works how you'd hope. So if you take the dot product of two vectors, it doesn't matter which vector's first and which one's second. And that makes sense. We look at the definition. If we just swap these, it doesn't matter, right? We're just multiplying the numbers together and adding them up. It also behaves nicely with addition. That should be a B. So you've got the dot product of two vectors being added together. So adding them first, then dot product. This is saying, hey, you could do the dot products first and then add them up. Do it in whatever order you want. Now, this is important though. This here is adding vectors. This here is adding numbers. So, you can do addition of numbers or vectors in either order and you'll get the same result, which is interesting. It also works nicely with multiplication or scalar multiplication. So if one of your vectors is being multiplied by a number, well, you can pull that out and do the dot product first if you want. Now, why would you ever care about that? Well, take a look at what we're doing here, right? We're sort of doing this sort of multiplying and adding up. Well, what if all of these had a fraction in it, right? Like all of this was over 5 or something. Well, trying to do this while it's all over 5 is annoying, right? So what this is saying is, hey, if you have an annoying fraction, you can just pull it out, right? And then do it at the end. So if every vector had a 1/5 in it here, pull the 1/5 out, and then at the very end, do it. Just makes it a little easier. And this one is a very useful property. So if we take the dot product of a vector with itself, it's always at least 0. It's never negative. And that makes sense, because if we look at this definition here, this is saying, hey, do this sort of thing, but now these are the same number. So it'd be u1 times u1, which is u1 squared, u2 times u2, which is u2 squared, and so on, right? Squaring means that the number's positive, and it's not going to be negative. So we're adding up a bunch of positive stuff, or not negative stuff, and so we'll get something that's not negative. Makes sense. But this thing is only 0 when u is 0. It is the 0 vector. So that's kind of useful for just, let's say you're writing an algorithm and you're like, well, I want to omit situations where this vector is 0. Well, if you've already computed the dot product and it's not 0, then you know this thing isn't 0 either, right? If you're working with both the vector and the dot product simultaneously, they're either both 0 or neither of them are 0. When you're doing a dot product of a vector with itself, to be clear. Over here, we cared when it was a vector dot with another vector. Here, it is specifically a vector dot with itself. And so actually, we're going to leverage that fact because we also want to talk about the length right? We've got dot product and length. This whole time we've been talking about these vectors as a concept that has both a direction and a length, and we have no way to meaningfully discuss a length yet, right? Like if I drew a vector from me to that door, how long is that? Right? How do I actually calculate that? Right? Because if we're going to talk about a length, we need some way to numerically find it. So turns out we can actually leverage the dot product here. So length I have to write it again. The length of a vector. So I'm going to write it again in general terms. This is the general forms of all this stuff it's something that's very overwhelming at first until you do examples. It happens every term where students watch these sorts of lectures and they're like, oh God, I can't. This is too much. And then you actually do the exercise and you're like, wait, that wasn't so bad, right? Because it ends up being adding and subtracting and multiplying like integers, right? It's the hard part is understanding, translating this into what you actually have to do. The actual doing part is like it's very simple. I promise, trust me. Which is everything a math instructor would tell you, of course. Notated. Got these double bars. So how do we find this? Well, we're going to cheat and use the dot product. Right here, we said that if we take a vector and dot it with itself, it's never negative, at least. So that means we can take the square root of it. Right? This is never going to be negative, so this is totally fine. So what does this end up looking like? Well, if we have a vector that looks like this, we're going to do this number times itself. So u1 squared, plus the second number times itself, and so on. And you've got all these things squared. Now, if you have a very good memory for high school stuff, this formula probably looks like something you've seen before, where you've got a bunch of numbers squared, added up, and then you take the square root of it. The distance formula between 2 points looks very similar to this from high school. So that's not a coincidence. That's actually good. We want that because then we can connect this concept to that. Well, let's just do an example here of just using this. So let u equal 1, 2, 3, why not? Random vector. I mean, it's actually distinctly unrandom because I just wrote down 1, 2, 3 as a sequence. So we've got this length that we're interested in. So how do we do this? Well, there's a formula for it, right? Although thinking in terms of this formula is less good than just knowing that if you know what the dot product is, then you just do this times this plus this times this plus this times this. You don't have to think about the formula. So 1 times 1 is 1 squared. 2 times 2 is 2 squared. Plus 3 squared. So that's 1 plus 4 plus 9 square root of 14. This is the number, right? So that's good because the length gives us a number, and you will have square roots a lot. But it doesn't really matter because, you know, when it comes to lengths, well, what unit is this? It doesn't matter as long as if you're comparing two things, they're using the same unit, right? Is this meters? Is it centimeters? Is it inches? Who cares? As long as when you do it again, you're understanding it's the same unit, right? And then you just have to compare them. Oh, one is twice as long or something like that. Okay, so some properties. Most of these are, again, not a surprise. this length is bigger than or equal to 0. Why? Well, we defined it in terms of this, so that makes sense. Also, the length is 0 when the vector is u0 itself. Again, from that. But an important part of length is if we, scale a vector by an amount, like if we made it twice multiplied by 2, we would expect the length to be twice as long. So it turns out that is exactly what happens. Except we have to take the absolute value, and that kind of, it makes sense for multiple reasons. One, if it were a negative number, then all that does in terms of vectors is it moves it in the opposite direction, but still scales it by that amount. So if you had -2 there, it's twice as long, just in the different direction. So we wouldn't want to say it's -2 the length, right? That doesn't make sense. We would just say it's twice the length. So that's why we've got this absolute value sign here, right? To get rid of the sign. So we only care about the actual magnitude. But also, if we think about it, we square everything. So that number is going to get squared a bunch. So if it were negative, it's going to turn positive, and then we're going to factor it out. So that's another reason why. But this gives us distance. So the distance between two vectors u and v so it's actually a pretty simple formula in terms of what we've already defined. It just says, hey, take the length of u minus v, right? Okay, we're saying this is distance though. So we should probably justify that, right? It's not immediately clear why this thing here somehow represents distance between vectors, right? What's the connection? Well, we can draw a picture. And I think that's probably the best way to do it. And in my notes, I have like a nicer looking picture because I can't really draw it super well. So we've got our vector. Let's call it u. Actually, I'm going to call this one v for make it easier. And then we got this vector over here. Let's call that u. Now, if we want to draw a picture of u minus v, what we have to do is we draw minus v, right? And then in this case, because of the way it's connected, I'm going to do the parallelogram law. So we draw this parallelogram, go across like this, and that's u minus v, right? Okay, but one thing we can do with vectors is we can pick this up and move it wherever we want, right? As long as it's the same length and direction, we can move it wherever we want. So let's pick it up and move it here. U minus v. But hey, wait a minute. What we just said is this is the distance, is the length of u minus v. This is u minus v here. It starts at the end of v and goes to the end of u. So this matches distance intuitively, right? Like if I just threw a rope that way and said, okay, just measure that, then that's the intuition for what length is, right? It's just, or distance. It's how far am I from that? Well, it's the length of a line from me to there. Right? I mean, well, okay, not accounting for tables. I'm not going to walk over tables. But if we remove the tables, that's what we would mean. So, okay, that means this actually matches our intuition. Okay, so another reason why this matches up is, so from high school, we have a formula for distance between 2 points, x1, comma, or y1. And they might have used different notation in high school. They might have called it xy and then like r and s or something like that. So there's a formula for this. It's x1 minus x2 squared plus y1 minus y2 squared. So that gives us the distance between 2 points. But if we just took two vectors starting from the origin, which connect to the point, then these two formulas are the same thing, right? So that's another reason why this definition makes sense, because this is the ye old high school diploma boring definition for distance. This matches that. So again, it really captures distance. So let's do an example. So let's let u be the following. 1, 3 minus 4. I need to actually steal these exact numbers for reasons. 1 minus square root of 3, 1 and minus 1. So those are just two vectors, right? It's fine that there's a square root in there. That doesn't matter, right? It's just a number. So then the distance between these two things, well, what's that? So it's the length of u minus v. Okay, that tells us first we have to find u minus v. So what's that? U is 1, 3 minus 4 minus this thing. Okay, so we just combine these things. 1 minus root 3, 3 minus 1, minus 4, minus negative 1. Okay, so we just number crunch. 1 minus 1. Okay, so those go away. That turns into a positive. So that first number is square root 3. This is 2. Minus 4 plus 1 is minus 3. All right, cool. So that's u minus v. So now we take the length of it. So that's the square root of this thing dot with itself. So square root of 3 squared plus 2 squared plus minus 3 squared. All right. So that becomes 3 plus 4 plus 9 is 12, 16, which is 4. It's a nice whole number. That's 4 meters or 4 centimeters, whatever. The unit doesn't matter. One thing to note here, and this is another common mistake. So notice that this thing is minus 3. Remember, it's minus 3 times minus 3. So the most common mistake that students will make is they will instead write this as minus 3 squared. And so then they'll end up with minus 9, which no, all of these numbers are positive. So remember, it's brackets around that, like that. So all of the numbers in there should be positive. Okay. Any questions so far? I know it's a sleepy Monday math. I hate the winter sucks. It gets so dark out. It's just so tiring. But so far so good. Yeah, I mean, okay. So a lot of these concepts, the kind of worst part about it, in the moment when you're learning it, is it's a lot. It's overwhelming. There's a lot of concepts. There's a lot of terminology. There's a lot of variables swinging around everywhere, and that can seem very overwhelming. But the good news is, when you actually do problems, my experience, students don't find them that bad. They're like, oh, I get it. It makes sense. And then you get the satisfaction of like, hey, that looked really complicated and I did it. And that's nice, right? We love solving a problem that seems complicated. And then ends up being not so bad. Okay, so what time is it? So I'm going to start talking about what I would say is the main meat of linear algebra. So we have these vectors, and we have another thing called systems of linear equations. And it turns out there's a lot of connection between those two things. Linear algebra is sort of the marriage of them. So systems of linear equations. So we're going to talk about a bunch of definitions first. A linear equation is of the form. So you got some numbers in front of some variables. That's all this messy thing means. How many guineas? N, yeah. So again, just numbers times variables plus number times variable plus number times variable, and so on. Equals some number. So these A's, A1, A2, are called coefficients. This guy right here is called the constant. And naturally, all these x's are the variables. So some examples. You've seen these types of things before. So 2x plus 3y minus 7z equals 2, right? This is an example of one. Again, this notation, ugly looking. It just means that you can have any number of variables you want, right? But here's an example of 3 variables, and they're nice variables. Another example. There's another equation, right? So linear just means number times variable, right? And then add them up. So pi is a number, right? It's just a number times a variable. Square root of 3 is just a number times a variable. If it looked like this, we would have a problem, because now this is sort of over top of the variable 2, and it is no longer linear. But so long as it's just the number, we're good. So some nonlinear equations. There's generally 2 standout things that make something nonlinear. If you just think in terms of what do they graphically mean? Linear, flat, right? Straight lines, right? It's flat. Nonlinear would be curvy. Anything that would have curvature. So if you had something like 3x with the square root plus y squared, again, curve, minus sine of z equals 1. All of these are nonlinear things. Square rooting the variable, squaring the variable, taking the sine of a variable. Not linear. Another example that would make things nonlinear is a variable times a variable. Right? That's a situation where it's nonlinear. Now, these types of equations are interesting in their own right. We care about these. But we care about these a lot more often in like calculus and stuff like that, because these are graphs of surfaces and whatnot. And we're talking about like heat distribution or tension on something. Usually those are represented by equations that look something like this. So we do care about those, but they're Very challenging to solve. And usually each of them require different techniques. Like this first one here, I just wrote it down. I have no idea how you would solve it. Algebraically, probably can't. So how do you solve it? You use numerical methods, right? You use a computer. Like that's the only way to do it. This one you can actually solve, but it doesn't really matter. So point is, we don't care about these for us, which is good because these are complicated and hard. These are not so bad. So I'm just gonna, we don't care. Those are bad. We don't want those. So a solution of a linear equation is kind of exactly what you would think it to be, is a vector that solves the equation. So what I mean by that is you've got something that looks like this. Right, it's just a list of vectors. This is solution, S for solution, where A1 S1 plus A2 S2 plus AN SN is equal to B here. So here, X is a variable, right? But here we're saying, no, these are actual just numbers now. Like they're actual real numbers that we're plugging in. So an example, well, let's take a look at this first one right here. 2x plus 3y minus 7z equals 2. So 1, 0, 0 is a solution. Why? Because when we plug these numbers in for the variables in order, it works. So 2 times 1 plus 3 times 0 minus 7 times 0. What's that? 2 plus 0 plus 0, which is 2, which is what we want. Right? So that's all we mean by a solution, right? Which makes sense. We just plug the numbers in and it works. So same as what a solution means to anything else, right? I'm just writing it down formally. Okay, but this is systems of linear equations, not just linear equations. So what's a system? A system of linear equations is just a set of linear equations. So, here I have 2 linear equations, right? Now if I just say, hey, they're a set of linear equations, I guess I would need them to have the same variables. So x, y, and z. Now we have a system of linear equations, right? We're considering both of these equations at the same time. That's all it means. So a solution to a system must satisfy all equations simultaneously. So an example, consider the following system. Plus 3x2 equals 0. You got this, all right? But we're saying this is a system. So that means if something solves the first equation, it better work for the second one too. 3 over 5 and minus 2 over 5. Does this work? Well, let's go ahead and plug it in. So 2 times 3 is 6 over 5. 3 times minus 2 is minus 6 over 5, so they cancel out, you get 0. Cool, the first one's satisfied. What about the second one? Well, this is 3 over 5 minus 2 over 5. So 3 over 5 plus 2 over 5 is 5 over 5, which is 1. Cool. Satisfied both. Okay, what about some other set of numbers? So let's do 1, 0. So plug those in. 2 times 1 plus 3 times 0. That's 2, which is not 0. Right? We don't even care at this point what happens to the second equation because this is not a solution. Whereas this is a solution. Right, so solutions are exactly what you would expect them to be, right? You can just plug them into all the equations and they work out. Okay, let's consider another one. 2x plus 3y equals 1. Actually, I'm going to write 0. 2x plus 3y is equal to 1. So this is a system. So that means whatever solves the first equation has to solve the second one too. So if we look at this, this isn't possible to solve, right? Because these are the same equation on the left, just these numbers are different. So that means whatever we plug in here has to equal 0 and 1 at the same time, which is not possible, right? So it's not possible. For 2x plus 3y equals 0 and 2x plus 3y equal 1 simultaneously. Right? This has a solution on its own. This has a solution on its own, but it doesn't satisfy both at the same time. So, no solution. So we have a name for this. So no solution. The word we use is inconsistent. And over here, if there is at least one solution, that's called inconsistent, so we call this consistent. This is the other reason why we often invent words in mathematics is if we notice we're saying the same set of words over and over again, we say, okay, let's call that something, right? We notice we were talking about systems of equations that have at least one solution a lot. So, man, it sure is cumbersome to say, consider a system that has at least one solution over and over again. So we just say consistent system. Same thing over here. A system that has no solution over and over and over again, we just say inconsistent system. How much time do I have? Okay. So I'm going to do an example here that I'm going to say immediately forget it, basically, because one of the questions here is, well, yeah, great. We've got these systems of equations. How do we find these solutions, right? Well, that's what linear algebra is all about. So let me pull up an example, because we can just use the methods we would have learned in high school, and they're fine. They'll work just fine, right? So what I mean is let's solve the following system. Plus 2x3 equals 0. x1 minus x2 equals 1. And 3x2 minus 2x3 equals minus 1. Okay, so the method we would use from high school for without knowing linear algebra is what's called isolate and then substitute. So we can isolate a variable and then substitute to eliminate it. And we just do that over and over again until we get a solution. So it does not matter what variable you pick first and what equation you pick first. So generally speaking, I just go in order, right? Like, let's start with equation 1. What does that say? Equation 1 is 2x1 plus 2x3 equals 0. Okay, so our step 1 is isolate a variable. Doesn't matter which one we pick. So let's isolate x1. So we're going to move the x3 over to the other side, divide by 2. And hey, we've got this relationship. x1 is equal to negative x3. What does this really tell us? It means, hey, in these remaining two equations, we can now replace x1. What do we replace it with? Minus x3. Right? It just, we can, every instance of it, we can make it go away. Now, what does that really do for us? Well, it gets rid of a variable. And it kind of gets rid of an equation too, because we just used this first equation to get rid of a variable. So we just have these two left, right? We've already used this one. So now we just need to use these two. So we can eliminate x1 from the remaining two equations. So what we have is this, and 3x2 minus 2x3 equal to minus 1. So this, we just plug it in for x1. So minus x3 minus x2 equals 1. Right, so this is our system left. But hey, now there's no x1 anymore, right? We've gotten rid of a variable. So now what do? We repeat. Pick another one of these equations and do the same thing. Pick an equation and then pick a variable. So I just like to go in order. So I'm going to go ahead and pick this equation. So minus x3 minus x2 equals 1. And since I dealt with x1, I'm going to do x2, just in order, right? Just go numbers. So we're going to move this to one side, or we can leave it on this side. Depends on how you like to think about it. So let's leave it here, minus x2. I'll move that over there. 1 plus x3. Well, let's get rid of that minus sign too. x2 equals minus 1 minus x3. Okay, how does that help us? Well, we can rinse and repeat. We can say, hey, now we have one equation left, and we can get rid of x2 in it. So let's go ahead and do that. So our last equation is 3x2 minus 2x3 equals minus 1. And like I said, we can now get rid of x2. How do we get rid of it? We replace it with minus 1 minus x3. So 3 minus 1 minus x3. And why does that help us? Well, again, we just got rid of another variable. The only variable that's left is x3. So hey, that means we can just solve for x3. So how do we do that? We just simplify. x3 minus 2x3 is equal to minus 1. Okay, collect these terms together and move that over. Minus 5x3 equals 2. Divide by minus 5. And hey, look at that. We just found x3. Well, how does that help us? Well, we can now work our way backwards. If we know x3, we can get x2. x2 is minus 1 minus x3. So minus 1 minus negative 2 over 5. That is, oh god, minus 3 over 5. Please don't check my numbers on this. I'm doing this off the seat of my pants. So point is, x2 is minus 3 over 5. Okay, cool. There's the second number. Now the third number, x1, is just, it's just minus x3. So 2 over 5. So now we know x1 is 2 over 5, x2 is minus 3 over 5, and x3 is minus 2 over 5. And that was awful, wasn't it? Like, really tedious, really messy, lots of moving stuff around, lots of keeping track of crap. That's the point. This is a terrible way to do it. I wanted to go over it, though, because this is the method we teach in high school. If you were told to solve 2 equations with 2 unknowns, this is what they want you to do. 3 equations, 3 unknowns, you do this. And I find that very interesting because the concepts we're going to talk about, I guess I get it. We're going to talk about a better way to do this, by the way. That's like way nicer to look at and way easier to understand. It does, I guess, kind of need you to understand that this is what's going on in the background, but it doesn't really. So I think it's interesting that we don't teach like some simple linear algebra stuff in high school to do this instead. But the point is, I'm not going to make you do this, which is why I said you're going to immediately forget this example, because we're going to talk about a better way. There is a better way to solve equations that uses linear algebra stuff, matrices, which is the thing that we care about as programmers because it helps us visualize multidimensional arrays, and it is really good practice for nested for loops, so loops inside of loops and that sort of thing. So they're very, very useful for algorithms and just programming. So that's why we care about it, but I just wanted to be like, hey, do you remember this method? If yes, it's bad. If no, good. Then forget about it already. And we're going to talk about a better way to do it. So with that, I will leave you on that example feeling like overwhelmed and disgusted by the mathematics I just wrote on the board, which is fine. And on Wednesday,